Here we have that D, A, and F are function of the input variable. And the next equation is a quadratic and the angle 3 divided 2 and can be used to find the copper angle 3. And this equation can be used to calculate the output and couple angles 4 and 3 as two functions of the input angle true provided to the legends A, B, C, and D are given. After by adding equations and simplifying, we derive the following equation, and we have J1 cos angle 4 is blah blah blah, where G1 have an correlation that we can see, and this is called a Freudenstein equation, and the Freudenstein equation to may be explained by using trigonometry. Below is an example where it's not necessary to draw a diagram since everything is going to be done by using the equations. Now we have then two possible configurations for a forward linkage at any angle 2 and for substitutable variables of A, B, C, and D equations. We are gonna use the equations that in the last diapositives we desire. Provide two valves for the output and coupler angles 4 and 3. Both solutions are possible and provide two different configurations for each input angle 2. A substitutable set of A, B, C, and D is the numbers that make the radicals in the equations. And as an example, consider a linkage with the following legends. Now we have the equivalence, and the desert is the equivalence that we have in the right side, and we have the coefficients of the quadratic equation are then calculated. So in this diagram we can see the possible configuration of a forward linkage having the same input angle 2. Now we're gonna use the minus sign, the output and copper angles at 2 is the same than P divided 4 radians is the same than 45 deg, and this is the expression that the angle 4 is like 2 radians, then this is like 140.73 deg, and angle 3 is like 0.897 radians, and it is more like the same, 51.42 deg. And using the plus, we have then for angle 4 is more like 2.6 radians negative, and this is the same than 149 deg negative, and the same with the angle number 3. And now Uh, we can see that depicts the two possible configuration of the linkage for the angle 2 is always 45 degrees. The configuration in the figure is called convex, not corset or evolved up, and the configuration in the figure is called concave, crossored, or evolved down. Now here in this picture we have another example. This is a demonstration simulated a classical trapezoidal steering linkage of a car with front wheel steering. In order for the inner and outer front wheels of a car turn with splitting in a curve, the steering angles to complete with the Ackermann condition. This condition ensures that the turning circle of the both wheels their center on the same horizontal line defined by the real axis. We can see that an upload shows how close a trapezoidal linkage can approximate the Ackermann ideal given the right geometry of the car and the linkage. In conclusion, I think that the importance of knowing how to calculate and know the movement of these machines gives a broader vision to be able to visualize the internal movement of the machines, and it is a copied machine since the movement affects each bar or linkage, but that does not mean that all the linkage or bars have the same stern or spout. I think that this mechanism requires an in-depth study since it usually confusing and in its application. Thank you very much.